Okay, so the orchestration code wrapping your LLM now drives more performance variation than the model itself. Same model, 6 times the performance gap, depending entirely on the wrapper or harness around it. That's the headline finding from 2 papers from Stanford and Tsinghua University. And it means that the entire which model is the best debate has been wrong question for a while now. Now, in this video, I'm going to walk you through 3 things. First, exactly what a harness is and why it matters more than the model itself now. Second, the 2 papers from the Tsinghua and Stanford that formalize this as a discipline that is known as harness engineering. And third, the practical takeaways, what specifically you should change about how you build agents starting today. By the end of this video, you will know exactly which levers to pull when your agent is underperforming. And I think you will find it's almost never the lever you are reaching out for. Okay, so let me break it down for you. In simple terms, a harness is an architecture that turns a model into an agent. The agent itself is just a one-shot text generator. You ask, it answers, and then it stops. The harness is what gives it the ability to take actions, see the consequences, and keep going until the problem is actually solved. Now, there is a really clean way to think about this, and it's an operating system analogy. The raw LLM is the CPU, which is powerful but inert. No memory, no storage, no I/O. Your context window acts as RAM, which is fast but limited. External databases serve as disk. Tool integrations are device drivers, and the harness is the operating system, deciding what the CPU sees and when. And I think this analogy actually maps really cleanly onto the 9 harness components I covered in my previous video. Now, here is why this matters for today's video. My previous video answered what a harness is. What this video is about is something different. Why is the same harness producing 6 times performance differences depending on exactly how those components are structured? Okay, so let's look at the first paper. And this is where it gets really interesting. The first paper is from Pan and team in Tsinghua University, which was published in March 2026. They asked a simple question: what if you could write an agent's entire control logic, not in Python, not in YAML, but in structured natural language? The structure has 3 layers. At the bottom, backend, the actual infrastructure, and tools. In the middle, what they call the runtime charter, which is a universal physics, basically how contracts bind, how state persists, how subagents or child agents are managed, and on the top, the natural language agent harness itself, which holds the state-specific logic. These include contracts, roles, state structure, and failure modes. Now, why does this separation matter? It gives harness engineering controlled experimentation. So you can swap the harness while fixing the runtime, and you are testing harness design in isolation, which gives you clean ablation. Now here's where the results get interesting. On Sweetbench verified with GPT-5.4 at maximum reasoning, the resolve rate clustered around 74 and 76% regardless of the configuration. But the full harness burned 16.3 million prompt tokens per sample. You're talking about more than 600 tool calls with more than 32 minutes runtime. But then they stripped down a version of this, which used 1.2 million tokens, 51 calls, under 7 minutes, same destination, 14 times the compute for the same result. They did a module by module ablation, which means that they started removing or subtracting parts of the system. Self-evolution was the only consistently helpful module, verifiers actually start hurting. They saw minus 0.8 on Swebench, minus 8.4 on OS World. So multi-candidate search hurt by 5.6. More structure is not always better, which is kind of a surprising result. But if you think about it, it kind of makes sense. I'm going to come back to this in the practical takeaways, but the headline results from this paper came from a different experiment. They took OS Symfony, a native code harness for desktop automation, and migrated its logic into natural language representation. Again, they use the same strategy, but just rewritten in natural language. And in this case, performance jumped from 30.4% to 47.2%. Runtime dropped from 361 minutes to 141 minutes. LLM calls collapsed from 1200 to 34. The representation itself drove the gain. That's a really significant finding. Now, keep this in mind, but let's look at this other paper, which was released by Umar Khattab, who built DSPy. And they took it one step further. If representation matters this much, can we find the right harness automatically? A quick word from today's sponsor. If you're building production systems that need to access data available on the web, whether it's a RAG system or an agentic system, you probably have noticed that as you scale up, some of the requests are going to be blocked. It doesn't matter how good your logic is. If the IP gets flagged, the data stops moving. The fix is to have good proxies. This is where today's sponsor, Data Impulse, comes into play. The residential pool is honestly hard to beat on value. Pricing starts at $1 a gigabyte, and what you buy does not expire. On top of that, over 90 million ethically sourced IPs across 195 different countries. If you're already running Scrapy, Playwright, or Puppeteer, they have got full integration guides on each one right in their docs. So you can wire their proxies straight into the applications that you are already building. And if your app needs mobile traffic, you can swipe right over that. There is a dedicated mobile pool and your script barely changes. You're using the same auth, same call, a different endpoint, and you're routing through a phone class IP. Link is going to be in the description. If you're shipping a data pipeline, needs IPs in specific city, or you just want scrapping to stop being a daily fight, take a look. Now back to the video. Again, it's structured, retrieval, memory, orchestration topology. It controls everything. Now here's how the loop works. The agentic proposer, in this case they used Claude Opus 4.6, reads failed execution traces, diagnoses what broke, and rewrites the complete new harness. The final scores and raw traces accumulate in a growing file system, and the loop repeats. The scale here is what makes this work. We're looking at 10 million tokens per iteration, 400 times more feedback than any prior method. It's reading about 82 files per round, and those raw traces are irreplaceable. When they removed them, accuracy dropped from 50% to 34%. When they replaced traces with summaries, 34.9%. This signal lives in the raw details. If you summarize prior failures and just feed those into the model, it could hurt the performance of your agent. Now, the results. Rank 2 with Opus, rank 1 with Haiku. So in this case, a smaller model outranking larger ones through harness optimization alone. The numbers are 76.4% on Terminal Bench 2, the only auto-optimized system in a field of hand engineer entries. On a 215 text classification, it was scoring 7.7 points above state of the art using 4 times fewer tokens. But here's the finding that I think is going to be significant. A harness optimized on one model transferred to 5 other models. and improving them all. So think about this. And what exactly does this mean? The reusable asset is not the model, it's the harness. You can build it once, it works across the model landscape. Now, I don't want to generalize it too much. Now, this all might sound academic until you map it onto something you have probably already noticed yourself. Take any frontier model, say Claude Opus 4.6 or 4.7, GPT-5.4, or even Gemini, doesn't matter which. Run the exact same prompt through it inside Claude Code, then Cursor, then Anti-Gravity. And the idea is that you keep the model exactly the same, you just change the harness. Now the prompt needs to be relatively complex, but you're going to see noticeably different results. You're going to see different reasoning paths with different token spends and potentially different success rates. And all of this is driven by not the model, but the harness that you are using with the agent. Opus 4.7 behaves very differently in Claude Code than inside Cursor or other third-party harnesses like Open Code. Okay, so the most important practical takeaway from all of this, and the one I think most builders are getting wrong, is what Anthropic calls the subtraction principle. So every harness components, and remember in my last video, we walked through 9 of them, encodes an assumption about what the model cannot do alone. And those assumption expires when the models improve. When Opus 4.6 stopped needing context resets, Anthropic just dropped them entirely. Manus, the agent platform, rewrote their harness 5 times in 6 months. Vercel removed 80% of the agent's tool and got better results. That is pretty significant. So, now, here is what it means. Mature harness work looks less like building structure up and more like pruning it down. In the last year, the idea was to provide agents more and more tools, but that is going away. Simpler is much better. A craft of subtraction as much as addition. Tsinghua ablation we just looked at really proves this. Sometimes the verifier can actually hurt your agent a lot more than it can help. The way you want to think about it is that if the model is able to do an aspect that was handcrafted in the harness before, you want to simplify your harness and drop that specific tool. Now, if you're building an agent, you are a harness engineer, whether you call yourself or not. So when you run into something that is not working, here is the order of operations I would suggest. Don't switch the model first. Audit the harness. And here are 4 questions that you can ask yourself. 1, what's in your context window that does not need to be there? 2, which tool do you have that the agent rarely uses well? 3, are you adding verification or search loops that might be hurting performance, like the Tsinghua University found? And 4, is your control logic written in code or in language? Because the migration experiment we looked at before showed almost 17 points gain just from rewriting the same logic. And it's no longer a question of which model to pick, it's a question of which structure to remove. Anyways, I hope you found this video useful. Thanks for watching, and I'll see you in the next one.